Welcome to Triomeet. Let's solve exercise problem 2.19. The principle of parallax in section 2.31 is used in the determination of distances of very distant stars. So the parallax, we've learned the formula d is equal to b by theta. The baseline AB is a line joining the Earth's two locations 6 months apart in its orbit around the Sun. So we've got the Sun here. We've got the Earth orbiting around the Sun. So 6 months apart. So the star Earth will be at this position next. So this is distance AB. That is, the baseline is about the diameter of the Earth's orbit 3 into 10 power 11. So according to this, the distance between the Earth 6 months apart, d is equal to 3 into 10 power 11 meters. However, even the nearest stars are so distant that with such a long baseline, they show a parallax only of the order of 1 second of arc or so. You've got a star here. It shows a parallax of only 1 second of an arc or so. A parsec is a convenient unit of length on the astronomical scale. It is the distance of an object that will show a parallax of 1 second of arc from opposite ends of a baseline equal to the distance of the Earth to the Sun. Distance of Earth to the Sun, parallax angle. How much is the parsec in terms of meter? This we've got theta here. So this distance will be equal to d by 2. So b is equal to d by 2. Theta, they've given it as 1 second. Theta is equal to 1 second. 1 second of an arc from opposite sides. Okay, so they've given a parsec is a convenient unit of length. It is the distance of an object that will show a parallax of 1 second of an arc from opposite ends of the baseline. So they say a parsec. So actually d is equal to 1 parsec. But we need this in meters. We need to know how much is this in terms of meters, right? So from the formula, we said we know d equal to b by theta, right? So what is b here? D by 2. Theta is 1 second. We need to find what d in terms of parsec is, right? So d is equal to b is 3 into 10 power 11 divided by 2 into 1 by theta, that is 1 second. We need this value in radians. Now how do we do that? We saw in one of the videos, and this is one of the examples in Ncert. It shows us how to convert 1 second into radians. This is basically 1 second will be equal to So this is how we convert from 1 second to radians. So this is given in one of the videos. Do refer to that. I'll put it in the link. So basically 1 second is equal to this thing. That is otherwise 1 by 60 into 1 by 60 into pi by 180. So inserting this value right here, we get 3 into 10 power 11 by 2 into 4.85 into 10 power minus 6 radians. So we get the d in terms of parsecs to be equal to 3.0. In terms of meter, we'll get the value to be 3.08 into 10 power 16 meters. So we know that this d is equal to 1 parsec, right? So we get the final solution to be 1 parsec is equal to 3 into 10 power 16 meters. This is our final solution. This is what we were supposed to find. How much is parsec in terms of meters. Let's solve question 2.20. Let's read the question. The nearest star to our solar system is 4.29 light years away. How much is this distance in terms of parsecs? So that's the first question. 4.29 light years in terms of parsecs. So let's solve this first. So from the previous question, we know that 1 parsec is equal to 3.08 into 10 power 16 meters. How much is 1 light year equal to? 1 light year is equal to 9.46 into 10 power 15 meters. Now I have to convert this into parsecs. Okay. So we've got, in the question we've got 4.29 light years. So therefore this would be equal to 4.29 into 9.46 into 10 power 15 meters. Right? Substitute 1 light year here. So now we've got it in meters. But our question is, we need it in parsecs. So how do we do that? Okay. So from this, what do we know? From this we get 1 meter is equal to 1 by 3.08 into 10 power 16 parsec. Right? Therefore, we can convert this into parsec. How do you do that? We divide it by 3.08 into 10 power 16, because right now we've got 10 power 15 meters. Now we have to convert this into 1 meter is equal to 3.08 into 10 power 16 meters. Right? So we get this in terms of parsec. Therefore, we get the final answer to be 1.318 parsec. This is our answer. Now let's see the next part of the question. How much parallax would this star show when viewed from two locations of the Earth 6 months apart in its orbit around the Sun? So, we've got the Sun here. We've got the Earth orbiting around the Sun 6 months apart. We've got Alpha Centauri here. This is a star. It is 4.29 light years away. So from two positions, that's a question. Okay, so we have to find out the parallax from the two different positions of the Earth 6 months apart. So this is theta. This is also theta. So the total parallax angle that we have to find is 2 theta. So we know that 1 parsec gives us 1 second, right? If it was 2 parsec, our theta would be 2 seconds. Therefore, here our theta would be 2 into, what is theta? Theta here is 1.318, which we can round it off to 1.32. We'll get the value to be 2.64 seconds. Here 1 parsec will give you 1 second. 2 parsecs will give you 2 seconds. Therefore, 1.32 parsecs will give you 1.32 seconds. This is according to the definition.